Hello. Hello.
Good afternoon, sir.
Good afternoon. Okay. Pavitra, can you take the attendance?
Yes, I will take.
Okay. All right. And please take the attendance at the end also, right? Or middles, whenever you get time. So,
Yes, sir. Okay.
very few students have come today. Uh, oh, nevertheless, let's start. Okay. So, today we will look at parallel computing in general. All right. And please feel free to ask me question at any point in time. So today we will finish our course, and Monday we will do the revision if you guys want. Okay. All right. So these are the references. Okay. And we know that Moore's law is slowing down. Okay. So the basically in Moore's law, what we have discussed is that the number of transistors we could pack were doubling almost 18 to 24 months, right? And we have seen this curve, after 2005 is not any longer in the same way. It's kind of flattening out. It's not totally flattened, but it's still flattening out. Okay, and this is what we have seen. And as a result of that, programmers got the free lunch. Okay, but after 2005 or something, it's kind of is not same as it's not going in this direction. And the reason for that we know, right? And reason for that is obviously two that we have seen. Uh, First was power wall, and of course, many people say memory is also not keeping pace with it. But main is that power consumption was very high. Okay, and then that results into the heating of transistors, right? And also, second thing is there is also technology limitation because we already reach almost 5 nanometer uh, size for transistor. You can't you know you can't make it zero, right? So now the reduction will be very very slow in the sense that now more packing will happen, but from 5 nanometer maybe one can go down to say 3 nanometer or something like that. Nobody knows exactly right now. Okay, so now still you want more performance. Okay, so we got the higher and higher performance because of Moore's law. Technology was improving. Now we don't have Moore's law anymore. It's kind of flattening out. Then what do we need to do? First solution is domain specific hardware. I mean, see, we have been making general purpose processors mainly, like in your laptop or desktop or servers. We have kind of processor that can do any kind of job. Now we can design computer to do one task very well. Okay, uh, just one task. Okay, and you can design the orient the whole data path, control path, that is processor design, etc. Number of processor, superscalar architecture where there are number of parallel pipelines. All that you can do for a domain. When we say domain means what? What do you mean? What do we mean by domain? Anyone? Or a set of problem, right? Of similar type. We can say, for example, you know, uh, say for example, DSP algorithm. Digital signal processing algorithm is one domain, or we can say image processing is another domain. Okay, then you can say AI and deep learning is another domain. You can all and so these are very specific set of problems that you can solve with a computer, and you design computer for that. Don't design computer then for word processing that can also do video conferencing, also do you can watch movies and so on. So the computers that we use is general purpose computer, which can do any task. So it's not optimized to do one specific kind of task. If you optimize hardware software for a domain or a problem type, then you can achieve efficiency. Right? All right. Uh, so for example, so these things can do few tasks very well, and we have seen. Then we can create processor of that kind. Okay, for example, we can design a processor for weather forecasting. That's it. The whole purpose is the input will get weather inputs or some data inputs, and then out will be prediction. So these are extremely complex but massively parallel processors that we can design specifically for one task. Or when we are firing a missile, we are not going to track missile firing through a PC. Okay, it has to be real-time system that will work at very fast pace specifically for one application. All right. So what is an example of this in everyone's computer, which is very domain specific? Look, your laptop, is anything designed very specifically for you or a specific task? In general, we can say no. But you still dig deeper, then you will find that yes, it has GPU. Okay, which can do graphics or graphics. We used to say graphics, but it can do a lot of other things now. All right, so these are very in general machines that we use is very general purpose machines. Of course it may have GPU for, because manufacturers assume that most of us will be doing heavy video processing, or at least screen should be screen will have high resolution and so on. Okay, but and also for gaming, now you can get gaming PCs nowadays, right, specifically designed for gaming with high-end GPUs. Okay, but apart from that, most of the computers that we see today, for example in your lab, whatever servers we have, these are all very general purpose machines. Even for example email servers that we may have in your in IT department are very general purpose, because in general email processing or email server doesn't require any very specialized kind of computations, right? So all right, so you can design that. What else can be done to improve performance? Okay, of course we need to exploit parallelism, and we know about it, right? That we have most of the tasks that we do have some part which is sequential, some part which can be parallelized. So then let's parallelize something that is parallelizable. Okay, and then again we come back to the same graph. We know that after 2005 we kind of speed up reduced because of the reason that we know that we can't pack more transistor and the power reasons, etc. Then we can see the number of cores have started going up. Okay, instead of just single processor which is becoming more and more powerful, now we have multiple cores or multiple processors. So what we nowadays do is exploiting parallelism. Okay, okay, so parallelism, we have been doing parallelism very often, right? Say for example if I want to peel 100 potatoes as fast as possible, they're all, and peeling potato is not data dependent, right? You can't peel second potato. Nobody says that you can't peel second potato until you peel the first potato. Okay, so one way is that you hone your skills and then start peeling them faster. That's one. Second is that get your 99 more friends, so you're 100 people and they immediately can peel it up, right? It will take just whatever time you will take to peel one, right? I mean, in my school when I was class 4, in primary school teacher used to give this. And when we learned, this multiplication and division, the first thing they say that in Hindi, because I studied in Hindi medium school, it's like this, that एक आदमी एक घास का मैदान 10 दिन में काटता है तो 10 आदमी इसको कितने दिन में काटेंगे इज एब्सोल्यूट पैरेललिज्म राइट बिकॉज घास काटना is there's no data dependency, 10 people can do it, of course, independently. Okay, so similarly, so now you cannot, every task is not parallelizable as much as, ghas katna or alu chilna. Then what we have to see what is parallelizable and what is not parallelizable. For example, I was thinking what could be example, right? You say to your mom, mom, 5 of my friends are coming, can you make dosa for them? Okay, and what will she say? Most likely, it cannot be done, right? As simple as that. Because starting from scratch, it cannot be done because some part is, even you assume there are 5 stoves and 5 people can make it parallelly, but certain steps, like soaking whatever dal and rice and so on, and then waiting it to ferment it, paste it and ferment it, it is all sequential. And once it's done, then of course 5 people can make 5 dosas at a time. Okay, so certain part is sequential, and then once you reach certain stage, then you can make 5 things at a certain. So now the speed up is limited to this part. This part cannot be parallelized, can't be. Okay, this part is parallelizable. So if you have a task, then parallelism can come only by either writing the task properly, which is parallelizable, okay, right in the beginning, or trying to find out what part of it is absolutely sequential, and then the remaining can be parallelized. And of course, there is a data dependency part that we have seen in pipeline, case of pipeline, right? Okay, all right. So let's move forward. So we have different types of parallelism, and first type we have seen already, right? Which is instruction level parallelism. It means that if there is a sequence of instructions, say instruction 1, instruction 2, instruction 3, and so on, you can, if there is no data dependency between the two, then you can parallelize, you can parallelly execute, say, I1 and I2. If I2 is not dependent on I1 and so on. Okay, so instruction level parallelism we have seen in case of pipeline. So these can be executed parallelly. Okay, so like superscalar architecture, if you have, at the input n instructions available, then first thing is do analysis and what can be done, executed parallelly, and then run them on different parallel pipelines. Okay, that we have seen. VLIW we have not seen, a very long instruction word, possibly we'll skip this. Basically packing multiple instruction right in the beginning into one instruction. Okay, we'll not get into it, but also apart from instruction level parallelism, we can also do thread level parallelism. Okay, so essentially what it means that execute independent instruction streams in parallel. So multi-threading is becoming extremely important, and I think all of you will learn multi-threading programming as part of your OS course. Okay, so once you create multiple threads of a program, then you can run these threads parallelly on multiple cores or on the same core, in, in multiplex way. Okay, uh, so concurrency arises from executing different threads of control in parallel. Now the question is that, do you know what is a thread? Have you come across this notion of thread in any course you studied so far? Anyone can tell me? Shivam, are you there?
Yes, sir.
Uh, did you come across the word thread?
Yes, sir. Can you
Thread,
repeat one more time?
thread, THREAD.
1 second, sir. There is been echo on my side.
Okay,
1 second, sir.
no problem. Have you heard this word called thread? THREAD.
Yes, sir. I have heard when I was doing a code. So whenever we compile something, it was written on the left hand side that this thread has been executing.
Okay, so what it is? How is it different from program or process?
Sir, 1 second, sir. There again, I have echo on my side.
So process is not a thread, right? Okay,
Yes, sir.
there is a difference between the two, right? You can say a thread is a process, possibly lightweight process, but there is a distinction between the two. I'm not sure whether you have been taught about it, but usually it comes in OS codes.
Sir, I
Okay,
think sub part of a process maybe.
no, it's not a sub process or process. Okay, all right, we'll look at it in brief, right? And then we have something called data level parallelism. Okay, and just a minute. All right. Okay, all right. Up. Okay, so we have data level parallelism, wherein we can have data coming in parallel. Okay, where instruction would be same. Okay, uh, so same operation, if we can concurrently apply to different pieces of data, then we call it data level parallelism. It means that you can, for example, we are doing add, say S1, S2, S3, for example. So S2 and S3 is data, and this is the operation. Okay, and then this, you are executing this in one processor or in one pipeline. Okay, now add is being issued, this is an instruction. Okay, uh, where data is different here, data is S2, S3. Can you run this on multiple processors together? Same instruction, but data stream here that's coming would be different. Okay, this is possible, right? This kind of computers you design, and for a very specific purpose, where data stream is continuously coming and you just execute one instruction. Similarly, this processor initially running add then can run something else, but all data are being operated upon same instruction. Okay, we'll look at this, right? So this parallelism that we have just now discussed, data level parallelism, will focus in this class. Okay, and there are large number of applications where we have data level parallelism, like graphics. See, what is the image that you are seeing on your screen? Okay, uh, is what? I mean, what is an image, right? It's nothing but pixels. Okay, and each pixel is being processed and mapped onto the screen, right? So that processing, image processing, that's happening to each pixel can be done in parallel, because there's no data dependency between the pixel, one pixel and next pixel and so on. Okay, so in general we can say that image processing can be, image can be divided in number of pixel, and how pixel is being formed, or what it is actually, whether it's any color or whatever combination is sending, may depend on some processing that's happening, and that processing can be done in parallel. So instruction is the same, where you may want to dim it, or or highlight something, but same instruction. Say for example, you want to reduce the intensity, or your screen to look whatever, right? Say of particular shade, then every pixel is going to do the same functionality, right? And it is exactly the same for each pixel, as it can be done independently. So instruction that is getting is same, but different pixel is having different data that are coming to it. Okay, and then we can do processing on different data items corresponding pixels simultaneously if we have corresponding processor available. So if you have as many number of processor as possibly number of pixels, it can be done just in one instant. Okay, so we call this is SIMD type of structure. We'll come to very soon. We'll learn about what is SIMD's architecture. And other is, of course, one type of SIMD structure is vector SIMD or subword SIMD, or we can have GPUs. Okay, that are also kind of SIMD computers. Okay, so before we study SIMD structure, which is becoming extremely popular because most of the general purpose processors are also extended with extended for SIMD computations, right? Let's look into Flynn's taxonomy. Flynn was a scientist. He I think in 60s or something, he came out with a taxonomy about how can we what are different types of modes of execution of program. Okay, in terms of parallelism. So he's defined actually classes of data level parallelism. Okay, so now he says that on the x-axis we have instruction stream. Okay, and whether instruction stream is single, it means that like one program, one is set of instructions that we have, say add, load, whatever. Okay, store or whatever. This is one single instruction stream. Okay, now similarly there can be single or multiple data streams. Okay, um, now in general we have yeah, in general we use instruction single data stream. Okay, so data stream can be single or multiple. Okay, and accordingly we will have corresponding designs, right? This is called SISD, single instruction single data stream. That our general purpose computer that we have is of this kind. Or we can have single instruction multiple data stream. Single instruction is executing on multiple data items. Okay, or we can have multiple instructions single data item. Multiple instructions are acting at a time on single data. Now this is only theoretical. And then we have multiple instruction multiple data stream. This is when we have multiple processes executing multiple programs or threads running different threads, and we can say we have multiple instruction multiple data stream. Okay, so let's look at the first one. Single instruction single data stream is nothing but sequential computer that exploits no parallelism either in instruction or data stream. So we have data is coming from data pool or memory, and instruction is coming from instruction memory, and we are executing that. There's a normal simple computer that we do. Okay, second is that we have multiple instruction and single data. You have just one instruction, but it's being executed on multiple processors, right? Now this is only theoretical. Or you think about it, I mean, you can of course may have some obligations that will require single data item to be executed onto multiple instructions. Okay, but there are not many examples of this kind. Okay, so this is usually not studied. Okay, and third and fourth type is most popular in parallel processing, wherein here you have single instruction multiple data stream. So for example, you have add instruction that is coming, but data on which you are operating, say S1, S2, and then moving to S3. So this value of two operands may come parallelly here, in different processes at a time. So you have data pool here. Okay, you may ask how this memory is able to supply that, because we can read it one time. Now here you assume that memory also can give data items parallelly. So here this may get, say for example, S1, S2, this may get S3, S4, S4, S5, S6, S7. And then they can parallelly execute, run add instruction and get the output. Okay, output can come out. All right, so this is so computer that applies single instruction stream to multiple data stream for operations that may be naturally be parallelized. Okay, so GPUs are generally of this kind, or SIMD instruction extensions. We'll look at that. Okay, and the fourth type is MIMD, multiple instruction, multiple data types, where you are executing multiple instructions on multiple data streams, right? Like you have multiple processes are running, and each process is requiring a data stream, and these are running on different processors, right? So you have different instructions coming, okay, on different one, and then your different data streams are also going there. It's not very clear from the diagram, but so it's multiple autonomous processes simultaneously executing different instructions on different data. All right. So this is normal. If you say that you have multiple computers connected to a LAN, and then of course input to that comes from a data pool, okay, which can supply all this, then then you can say it's my MIMD machine, or for example your data center or cloud computer, right? Wherein I am running my program while you are also running your program, and data stream for my program and your program could be different. Okay, and then we can say it's MIMD. So SISD of course has been there right from beginning. Okay, like normal old computer where everything, one instruction comes and one data and then execute, right? Your most of the computers fall in this category. Then something that is popular is SIMD, and then MIMD. So these two are modes of parallel processing. All right, any question up to this point?
So I have a question.
Yeah.
So suppose there is data dependency between the instructions which are running parallelly. So can SIMD and MIMD run properly? Because, for example, in SIMD, suppose the instruction running on the first processing unit saves the result in S3, and the instruction which is running on the next processing unit is using the same S3 register. So then
Yeah,
can
so then you, of course, these are the problems, right? These are of course problems. Then you have to find out either algorithms such that you can use this kind of computers efficiently, or you have to find out the problems that can be parallelized. Say for example, you are playing a video game, okay, and then and you have now you bought a new laptop that's kind of you know designed, or that's made to play video games in some sense, right? So that will have a GPU of a specific type. So your processor will send the computation, the main CPU will send computations related to vector processing or GPU kind to the GPU. Okay, so now something that you are playing is parallelizable. Okay, and that will go into the system. Okay, in this SIMD processor within GPU. Okay. So not necessarily everything can be parallelizable, hence the parallel processing in general is a difficult task. Okay. For example, now, I mean, whatever companies I have worked, there always has been requests from customers to make the program multi-threaded program. Okay, and this has always been a problem of people here because they don't know how to do multi-threaded programming. Now, once you do multi-threaded programming, which is thread safe, I mean, one thread is not interfering with another thread, then it can be easily parallelizable. Okay, because large amount of work of parallelizing is already done when you have created multi-threaded program. So now coming to your answer, yes, it's not, there can be data dependency. Then you cannot execute everything, every program, into SIMD machine. You'll have to see what can be executed. Okay, so these machines, even in the processor, normal computer that you buy, that's for game processing, part of your computation goes to SIMD part. Okay. All right.
Okay, sir.
We'll look at it again. So this is what it is, right? I mean, we have already seen that this SISD, SIMD, MISD, and MIMD. And Professor Michael Flynn of Stanford gave this classification. Okay, so the question is that when parallelism fail when problem inherently has some computation which is sequential in nature, right? This example of dosa making, of course, I have given in the beginning, but another example is that driving 10 separate car to get 40 people somewhere is faster than single car, right? Each car can take say 4 people, and you have 10 cars, and then all of you 40 people from your hostel can reach say movie theater together. Okay, but it does not reduce the time for each one of you. Okay, it takes the same time. Even if single car available to you, it takes the same time, right? So right, so we can't, and so because of this sequentiality in a problem which is inherently sequential, okay, you cannot achieve higher speed. Okay, now I am asking you this question. You want to brighten each pixel of a picture. Which class of computation is this? SISD, MISD, SIMD, or MIMD? I think I have already given the answer of this, right? Okay, Shivam, can you tell me?
Yes, sir. 1 second, sir.
You want to brighten each pixel of the picture or your screen. Now, this kind of computation, if you want to do parallelly, then which of this class of computation you will do? SISD, MISD, SIMD, or MIMD?
Sir, I think C.
Hmm?
The C, I think.
SIMD. Why?
I'm not exactly sure, but
Okay.
the single instruction.
Yeah, you should be sure if you focus, right, in the class.
Yes, sir. But
Devyani, can you answer it? Is it correct answer?
Hello? Yes, I think it's correct answer.
Why?
Because we just have to brighten every pixel. So there is
Yeah.
multiple data that needs to be operated, but one instruction.
Yes, correct. Basically, we are doing the same operation, so it can be done in parallel. There is no data dependency, right? Very right. Okay, so now we come to SIMD architecture. So basically, it's for data level parallelism. So, for example, you want to do this, right? Matrix multiplication. yi is equal to ci into xi, and where I is equal to 1 to n. Now, see, one instruction can be fetched here and then can be executed, right? For example, you can do multiplication here. So now all this can be done in parallel, right? So these are independent, right? So you can do this. So one instruction can work on different values of data, which is ci or c1 or x1, for example, and c2, x2, and so on and so forth, right? So now little complexity I am introducing here. Single instruction operates on multiple data elements in time or in space. So far we have assumed that it is in at same time, same instruction executing on different data items on different processors, right? Okay, so we have two kinds of time space duality, although most of the processors are combination of these. So we cannot, so these are what I'm telling you is theoretical in nature. Okay, so we have array processors where instructions operate on multiple instruction operate on multiple data elements at the same time in different spaces. So for example, as we gave the example of add, okay, add is executing on different data elements at the same time on different processors. Okay, so next would be subtract, then different data elements will come for that, for for each processor. So each processor will be executing sub and so on, right? And then we have something called vector processor where instruction operates on multiple data elements in consecutive time steps using the same space. Okay, so it will not be clear to you from this definition. Let's look at the example. This is the instruction stream that we are getting. Load, add, multiplication, and store. You don't worry about what this assembly language is. And then we have process. So first one is array processor, right? So here we have array processor where we have 4 processing element. Okay, now they can do any task, right? Can do add, load, multiply, and store. Okay, so we'll run load, same instruction, load will run on different processing element or processors. Okay, like this. Okay, of course they are getting we represented different subscript like LD0, 1, 2, 3 because these are is the execution on the first process, second process, third and fourth. Then data, of course, for this will be different. Okay, for each one of these. Okay, and what will once this is executed, it's not shown here the data that will come in. Okay, let's assume memory pool is there, they're supplying data. Once this is executed, then what they all will run? They all will run add. Okay, this one, second one. Then they will all run multiply, and then all will run store. What will happen in now? Look at in vector processors. Vector processor in general, we say when there are two vectors that we are executing. Okay, so here you see there is load element, then add element, then multiply element, and store element. It's kind of pipeline that we have seen. Okay, then we will run it in this way. Okay, so first load element will be here, and then this is time wise, right? First instant will execute load on first data stream, then we will have then we'll run load one and uh, add corresponding to this one here, add 0. Third instant will this unit will do load, this unit will do add, this unit will do multiply, and so on. It's kind of pipeline. Now we are what's the difference here? Just a minute. Okay, so difference is that see at this point in time we are in same operation at same time. Okay, now here we are doing the same operation, we are doing different operation at the same time. Okay, so this is and in the first one array process we are doing different op in the same space. It means the same processor is being used to do different tasks like load, add, multiplies. Here different, here the each processor or unit is doing exactly same task. Okay, so there is the way this is organized is different. All right, this is kind of pipeline that we have studied, right? But now in general we can have combination of these. All right, so something that is popular today is not array processor but vector processors. because now you can create deep pipelines, right? Now, but question is that are you getting the data exactly which is independent? If data is independent, there is no data dependency on the data that is coming in, then of course vector processor, you can create this kind of vector processor, and it will be extremely fast. Okay, so most of the SIMD machines, or I will say all, have vector processing and combination of vector and array. In general, we call it vector processing. Okay, so now onwards we will not discuss about array, but in general, when there is a vector, it means that there are multiple processing elements. Okay, now this processing element could be of different type, like as we have seen in this case. Okay, and they have parallel data streams coming into them, and they will execute. They will this different processing element could be same or could be different type, will execute on the instructions, data streams that are coming in. Okay, so vector processor is one whose instructions operate on vector rather than scalar values. And what is vector? Vector is one dimensional array of numbers that we know, right? So for example, A0, A1, A2, A3, or whatever. And so input is that stream, that array. Okay, and
Oh,
that, yeah. Okay, all right. So what we need to do in that case, we need of course vector registers where we can load and store. Okay, now we are thinking in terms of architecture, right? And vectors could be of different length. Okay, the input data that's coming in could be a say 32 bit or 6 or maybe more, or maybe 128 bits or whatever. Okay, then we have registers, we have to define registers very properly, right, for this activity. And then these are of course details. Then we have, in memory, where do we store these elements? Because the memories are supplying data streams, whether these are consecutive locations or after some gap and so on, and that's it's called stride. Okay, we'll not go into it. It's not really, see, in today's class, just want to give just glimpse of what these things are. We are not getting in detail. Okay, please try to understand the concept, that's all. Because the whole vector processing itself may take about 10-15 lectures. uh, all right, so we have vector processing model. So we have this is scalar register, while if we are doing vector processing, then we have vector registers. Now, the one task for you is that please find out the laptop that you are using has vector processor or not, or look at the specification of latest desktop and find out whether it will have vector processor or ability to do vector processing, or correspondingly vector registers. Now note that these vector registers, this is scalar register like the one we have studied so far, x0 to x31, right? In risk 5 we have studied that. Okay, here also we are assuming that if we have vector processor in this, then we'll have these registers v0 to v35. But now each register here, earlier case was 32 bits. Now we'll have many such 32 bits here, whatever. Each will be of 32 bits, for example, then it could be many. Okay, so basically the register length could be multiple of 32s, could be, I don't know how many it will be in case of somebody designs this 5-base vector processor. Okay, and then then the addition, for example, when we are doing addition, then this is first register, this second register, and then we can take data from different parts of that register, right? So this maybe first 32 bits can come here, and second 32 it can go to a functional unit, and then it can operate parallelly. So now this operation is happening in parallelly. Okay, and the results are available now. Is it becoming clear? Question? Anyone? Okay. Whom should I ask? Viranch Patel.
Sir.
Are you able to understand what is this happening?
Yes, sir. I mean, I have to refer to slides one again. Not that clear so much.
No, but what is not clear? So I want to just focus here. Focus. What is not clear? You tell me.
So I don't have, I mean, that confidence. So I have to refer to slides, and after that, it will be more clear to me.
Okay. All right. All right. Who can tell me? Yashi Agrawal.
Yes, sir.
Is it clear to you what's happening?
Yes, sir. I sort of get the feel what's happening, but similar to Viranj, that if I had a sort of that you said previous points like the brightness or and everything, so it sort of missed out that when new topic come. So if I can revise, if I can see the slides, and then
Yeah.
it would be better. So that's
Okay. So
um,
basically, all right. Thank you. So basically, what we are trying to say is that if we have a vector, you understand vector, right? It has n elements. Okay. If, for example, take array of size 10, okay, A0 to A9, and take array, another array, B0 to B9, okay, and when you do this, and I'm asking you to add these two and create array C, which is A0 plus B0 is equal to C0. Okay, how many steps you will take in sequential, your normal processor, right? You will get A0, then you will get B0, you will access B0, first you will access A0, you will access B0, do the addition of C0 stored somewhere, then second A1, B1 gets C1 and stored somewhere. Instead of that, what I am telling is that if your memory structure is such that you can get all this A0 to A9 in one shot, one step, and store this in register simultaneously, and second set you get it, which is B0 to B9, store this in a register which can store this, and then in third step you do addition. Now you will say that I can do addition if I have 9 such adders available. Okay, then in 3 steps you are done. Or rather, rather two, yeah, basically, yeah, 3 steps. I mean, first you get the values A0 to A9, B0 to B9 to register. Second step is that add, taking values from A and B. And third step is that you get the answers, store these values somewhere, right? So which is C0 to C9. So in just 3 steps you can get. Okay. So now what you are doing is vector processing. All right. Okay, it's
So
very
I,
simple. Huh.
so
Yeah.
I have a doubt. So the
Mhm.
vector processors, they process the same instruction in different timestamps, no?
So
Suppose the
it
instruction is
can do both. When you say different time instance, it can do also in the same time instant. The different, when difference is 0, it is the same time instant. Okay, so basically just forget about, right now you forget about distinction between array and vector processor. In general, vector processor operates on vectors. It means the registers will be of vector type, and then you have computation unit of that type. Okay, what I am giving is the simplest possible example. Okay, so basically we think of a vector as something which has number of which has certain, which kind of array or array of numbers, and then you can do parallel operation. Just think in those terms right now. Okay,
okay, sir.
let's not get into actually I shouldn't have introduced that term, but in general, okay, all right. So now we can do vector arithmetic, for example, just a minute. Okay, so the third part is that how can we load, from memory. If we have memory of this kind, then this register where we have different parts of register corresponding to different values that can be stored, so we can parallelly get the values from memory, uh, or memory. There are memory units we can think of, okay, and load from this register parallelly. Okay, so this is example of vector code. This C code, this scalar code, this is a vector code. Okay, and then we can do programming in which can do vector processing. We'll not go into details. Okay, so one advantage of that vector processing is that we can create very deep pipelines. Now the question you are asking is here that different parts of that pipeline can do different computation. For example, here this part can do addition, this part can do something else, say multiplication, this part can do something else. At the end, answer will be available. I'm just giving you some example, right? Or for example, you can create, okay, a better way of looking at is as follows. Okay, let's assume that we are doing this operation, v1 into v2. So we are getting v1 data streams from here, v2 from here. This, note that this is just one value we have got. After some instance, we will get second value. We have got one value from here. Okay, now this multiplication, okay, can we, if it's a, it will require certain steps. Okay, and these steps can be done parallelly, one after other. Multiplication in general of two numbers is, I mean, this is ALU actually, in some sense. So in general, we assume that we have not actually studied multiplication, right? When we studied risk architecture. But multiplication is not just single step operation like adder. Okay, so it will take number of steps. So now these stages can be done here. Okay, so now what you can visualize is that first two numbers, set you are multiplying 2 with 4, and till at the end here 8 will be available. Then second stream is say 3 and 7, then 21 will be available here, and the output will go here. All right. No, question you may ask is that how can this work? It can work only if you have this kind of data stream and this kind of algorithm where you have to do this kind of operation where data streams are independent, and uh, this kind of computation is required. Okay, now one advantage of that is that we can create very deep pipelines. And when we have deep pipelines, you have seen that we have in RISC-V we have 5-stage pipeline. And when we have moved from single cycle to 5-cycle pipeline, then cycle time reduced. As the pipeline length goes more and more, if you are able to increase the pipeline length more, then the cycle time that you can have reduces. You can use faster clock. Okay? And now this kind of processing, where data is kind of independent, right? There's no data dependency. Then you don't have hazards, right? We have studied hazards, control hazards and data hazards, right? So you don't have those hazards because of data dependency. Now you can, it's like a stream of data coming in one side and you are executing and answer is going to other side. As simple as that. Now this kind of operation you can do in case of say pixel processing or image processing. And what we have shown is just one instruction, right? Say V1 into the multiplication type, right? So you can have this kind of structures for various functional units. Okay, so there is another example. Okay, now instead of doing this in single functional unit, you can have multiple functional units, right? One here, shown here. Or here it's shown that they are doing exactly same operations, right? If your matrix size is big or vector size is big, then you can do, and these are all independent, then you can do it over multiple of such units, right, instead of one unit. Okay, so now you can see how vector processing can be done using multiple processing elements or functional units, okay, over independent data streams. Okay, if there is a dependency between, say, when result of this C0 and then should go somewhere and then you multiply it with A5 or something, then this cannot be done. Okay, all right, so let's move further. Whole idea is that why I have taken this up, because this becoming part of almost each computer today, right? Each computer will have vector processors inside. All right. So these points we have already discussed. Vector instruction performs operation on each element in consecutive cycles. Vector functional units are pipeline. Each pipeline stage operates on different data element. Okay, that we have already seen. Okay, and so deeper pipelines are possible, but what is needed is no intra-vector dependencies, no control flow within a vector. Okay, and that's all. Sites, etc. We have already seen, and there are some advantages, right? So advantages no dependency within vector. Okay, each instruction generates a lot of work. I mean, you just you fetch one instruction and do work on number of processing element can work on it. Okay, so your instruction fetch bandwidth require, it means number of instructions to be fetched reduces compared to single SISD or normal processor. Okay, because their same instruction is to be fetched multiple times, right? Okay, all right. So even in case of loop, for example, same instruction you fetch multiple times, right, as from cache or instruction memory. Okay, here we don't have to do that because data is coming in parallel, right? So it's very different kind of computation that we are doing. All right, so here the memory bandwidth can easily become bottleneck because we have assumed that all the data streams are becoming available. But if the memory is not designed for SIMD machine, then it could be a bottleneck. Okay, okay, so we say that array and vector processor, actually there's no distinction. So let's forget about array processor and think only in terms of vector process now. Okay, now this part says that SIMD extension, most of the conventional processor also have SIMD extensions. So this is now in 64-bit machine. We can assume that it has 8 units of, this is a register, for example. We can consider this as 8 registers of 8 bits. Okay, and then we have 4 registers of 16 bits. So we can take 2 registers and do operations on that parallelly using some functional unit. Okay, we are assuming here the space parallelism, right? Or there are multiple processing element available, and then that can do execution. And then in most of the processors today that Intel is coming out with, SIMD part is there. So it's a continuous evolution, right? From it started in 1999, and now, of course, I'm 2020. We'll have to see what it has, but it's increasing the instruction size. Sorry, the data size that it can operate or vector size is continuously increasing. Like here we have 256 byte vector, 256 bit vector, where here in the beginning we had only 64 or 120 bit. Now, so we'll not get into this. I just wanted to emphasize the fact that the whole technology is changing very fast. Okay, and vector processing is becoming part of normal, uh, a desktop even, right? Although pure vector processor you will find in case of GPUs. Okay, So GPUs are of course part of even is part of normal processor, and we have also separate GPUs like NVIDIA's GPU, and they all contain SIMD kind of processing unit. Okay, and these are basically Intel's advanced vector extensions. You will find that like all this chipset like Skylake or Broadwell or Haswell, all these have this vector extension. Okay, now here for example Skylake, you have 512-bit register, because once you have 512-bit register, it can be made some if each vector unit is 32 bits, you can divide this into number of units and do parallel computation. Okay, so just a minute. Okay, so we will just finish this in 10 minutes and take 10 minutes break, and then we'll come back and then we'll do second part of this presentation. Are you guys tired or okay? All right, so we'll skip this. So summarize. Vector or SIMD machines are good at exploiting regular data level parallelism. Okay. Of course, performance improvement is limited by vectorizability of the code. How much parallelism you can extract. Your algorithm, if the task that you are doing does not have any parallelism, it cannot be vectorized, then of course you can't do. I mean, if you have just 5 numbers to add, okay, there's very little parallelization one can do, right? And then first addition of first, it depends on first two, you are taking a sum and then adding with third and doing some multiplication. So if there is no parallelism, then all this process can be of no use, right? So did we cover Amdahl's law in the past? I don't think we have covered that, right? Anybody?
No, sir, we haven't covered it.
Okay, so just few minutes I will spend, then we'll take a break. Okay, Amdahl's law says make common case first. Okay, and don't waste resources on components that have little impact on overall performance. Okay, now we have used this Amdahl's law in case of cache. Now it basically says that I mean something that is being executed very frequently, you bring it to cache. Okay, don't bring everything to the cache. Okay, all right. The other point is that something that is sequential, then you cannot get any speed up from that, right? All you can parallelize is the part that is parallelizable. It's very common sense kind of law, right? So it says that performance improvements through an enhancement, say parallelization, enhancement, let's take a parallelization, is limited to the factor of the time the enhancement comes into play. Okay, so if you are making dosa, or it requires 10 hours, starting from 0 to 10 hours, and you take 8 hours for your sequential thing, whatever is there, soaking, grinding, mixing, fermenting, etc., and then you have just 2 hours available. Okay, so you can parallelize. Now you want to speed up this part, you can't speed up only this part. Now you have 10 people available, then you can then instead of taking 2 hours, which is 120 minutes, instead of that you can finish in 12 minutes, right? So overall time that you will sequentially you would have been taking say 10 hours, now you are taking how much? 8 hours and say 12 minutes, 8.12, let's assume. I mean, although it's not correct, but so what speed up you have got? 10 by 8 approximately. which is very little, right? So even if you put in 10 processors here, so this example, so another example is a web server spends 45% of time in CPU and 60% of time doing IO. Now, I note that IO can't be parallelized. What you can parallelize 40% of time, and then you have new processor which does 10 times faster work. Okay, then what speed up you will get? You will get, instead of 40 minutes, let's assume that instead of 40 minutes, you will do this work in 4 minutes. Now, but your 60 minutes is still required by IO. So instead of 100, you should be able to do work in 64. Although you have used 10 processor or 10 times faster processor. So putting 10 times faster processor, your speed up is just 1.56, is 100 by 64. Okay. So if task has serial part and parallel part, okay, and divide the input data into n pieces and do work on each piece and combine all results. So this is example. Then all you can achieve is because of the parallel part that you can execute. Okay, so this is a serial part, and this can be parallelized. Now, if you have 4 processors here, then time taken will be this much. If you have 8 processors, then time will further reduce. So only this part you can parallelize, but overall time still remains significant, right? So this is Amdahl's law. All right. So now question is that how much you can parallelize. Okay, and what we do is that in GPUs and multi-core architecture, if you want to parallelize, you parallelize threads. Okay. Okay, so I want to give some idea about what thread is. Okay, so multi-core architecture requires thread, and you will learn about thread more in your OS course, right? So what is a process? A program in execution, right? A process has multiple threads. Okay, so when we say, okay, program is single threaded process, okay, it means that thread will use code, data, files, okay, registers and stack. Same, because there's one thread, right? Okay, but threads share code, data, and files. Okay, data means the input data, but they don't share registers and stack. So basically, a process can have multiple instances of execution. Okay, and each is doing exactly same thing, getting data from the same set of sources, not exactly same data, but same set of sources. Okay, but they are not sharing registers and stack. It means that when we share registers, why we need, when we save a process, we have seen in case of an instruction, okay, JLR, etc., that we save registers and stack, because registers and stack gives the state of a process. So now we can run like, this multiple threads, basically same program execution, but maybe taking different, because each thread is doing different kind of work, or maybe same kind of work but different data items. Okay, so here is a thread, right? So we have now multi-threaded process, means that there are multiple threads of a process. Note that they have they are not sharing registers and code, but they have, here we can show the same code, data, and files. Okay, all right, so we will stop here, and then after 10 minutes we will study the last part of this course, that is on data center. Or if you are tired, if you want to skip this data center thing, then we can also skip.
Sir,
Yeah.
so, is it possible, can we have this session like tomorrow? Like, if some of them are tired, and we can like freshen up and do it tomorrow, like one hour class at 2 o'clock.
Okay, instead of tomorrow I'm held up. We can do it on Monday also.
Like if you agree and the class agrees with it, then
Yes, sir. That would be better instead of today.
Okay,
Yes, sir. I
so
agree with
shall we do it on Monday? Till what date you have classes? Monday is last day, I guess, right? Or Tuesday?
Sir, can't say. Sir, if it is possible, then you can take on this weekend any day, any means to which time the class agrees.
Okay, then you let me know. These what I'm going to teach you is not something is important part of the syllabus, right? Similarly, what I have taught today, SIMD, or some I have followed the course from Berkeley. They have taught this, and because it's becoming important, it's a part of a normal machine today. So you should know this. What is SIMD is? That's all the objective of this class, right? Which you have understood it, right? Of course, we don't have time to cover GPU, but it's kind of SIMD structure. Now, next thing that's left out is what is a data center again? Is something, if you know what the structure of data center is, it will help you, because I don't think any other course will cover that concept. So this is only for your own interest and information, and possibly help you in your job, getting a job. So not more than that. So you let me know. I can take 1 hour anytime. Okay, whenever you have time available, even during the weekend. I am fine. And last lecture I want to take is exactly on revising what we have studied so far, one after other, right? I mean, starting from first lecture, and we'll try to see sense why we have studied all that, and trying to get big picture, right, from that. Okay, that part is also, I think, important, because when we try to connect different things we have studied, you possibly get much clarity on the whole thing, right? Okay, so I'm fine. You let me know when you want this class to happen. I'm available. So, of course, where else we can go when there is pandemic. So you tell me Saturday I'm fine, Sunday I'm also fine. You just need to tell me when. Okay. Who will
sure,
tell?
sir.
One of you need to take responsibility.
I'll do it, sir.
Okay, all right. Just send me email and or maybe WhatsApp, right?
Okay, sir.
All right. Thank you very much. Thank you. Bye bye.
Thank you, sir.
Thank you. Bye bye.